We're now going to discuss the transpose operation. Now, you've seen transposition before. We've talked about a column vector, and then we've talked about how if you transpose that column vector, it becomes a row vector, and we used it as notation when we discussed the dot product. So let's have a look and see what it means for a matrix to be transposed. Okay, so the definition of transposition is as follows. If we have a matrix A and a matrix B, and matrix A is of size m by n, and matrix B of size n by m. So let's make a picture. A may be like this, where this is m and this is n. And then B looks like this, which is n by m. B is said to be the transpose of A if the ji entry of B is equal to the ij entry of A. Now, what does that mean? Well, it always helps to put a diagonal here and a diagonal here. And let's say we have some entry in A that's the entry ij. Then if you look at that same entry mirrored with respect to this diagonal here, then that would be the entry ji. And what it says is that the ji entry of B is equal to the ij entry of A. Okay, in that case, B is said to be the transpose of matrix A. Okay, now the transpose of a matrix is denoted by A transpose. Okay, so if you take A and you transpose it, then if B is the transpose of A, we can say that B is equal to A transpose. Okay, so let's have a look at an example. Here we have A. Let's highlight the diagonal here, and let's highlight the diagonal here. If you compare these two, what you notice is that, for example, this entry right here above the diagonal now becomes the mirrored entry below the diagonal in B. A is 3 by 4, then B is 4 by 3. Now, obviously, if you go and you transpose A and then you transpose A again, then you simply get A back again. So where have we seen this before? Well, we've talked before about X, and we've talked about the fact that X can be viewed as a column vector or as a matrix with only one column. If we view it as a matrix, then we can transpose it, and it goes from being a matrix with only one column to a matrix with only one row, and sometimes we'll think of a matrix with only one row as a row vector. Let's look at an algorithm that copies A into B, transposing it along the way. And we're using this notation with which hopefully you're starting to become familiar. Here on the right, we expose matrix A and matrix B for the specific example where A has 3 rows and B has 3 columns. Okay. Now, what happens? In our algorithm, we start by partitioning A vertically and B horizontally, where A left has no columns and B top has no rows. Then we expose the next column of A and the next row of B, and we copy the entries from the column of A into the row of B. So notice that the column of A is transposed into the row of B. Okay, this entry here came from here. This entry here goes there, etc. Then you move on. You expose another column of A and another row of B. You transpose the column of A into the row of B. You move on, and so forth. Notice our notation. B1 transpose becomes A1 transpose. Now, it's very important to realize that The transpose on the B1 has to do with the fact that it's a row of B, and the transpose is a label that labels this as a row. The transpose on A1, on the other hand, comes from the fact that you take the column of A and you transpose it in order to be able to overwrite the corresponding row of B with it. So in summary, if A has these entries, then transposing it means mirroring it with respect to the diagonal, and an entry, for example, down here, up here came from this entry right there.